Okay, so this is our first setup. Basically, in this problem, we have two setups. One, when the hanging mass travels just before impact, and then after impact. Because after impact, the mass on the table will still have inertia, and then the distance it takes to slow down to zero can give us the force of kinetic friction. Because if there was no force of kinetic friction, then after this hit the ground, this mass would just keep going. So what we did was first we set up a diagram for the initial setup, just where you have the hanging mass and your block is on the table. And we set up our little energy equations. So we have mgh, big mgh, so this is of this hanging mass, and then plus little mgh of this. This little mgh does not end up making a difference because at the end of this diagram it's still on the table. Our after equations, you still have this little mgh, as I just said, and then you have the kinetic energy of the whole system, which is 1/2 little m plus big M times v squared. Because this block will be pulling the entire system, so the entire system will have the same velocity. So then we set up our equations. So work done by a non-conservative force is energy final minus energy initial. So we put in this for energy final, this for energy initial, and then once again, as I said, these two mgh's cancel out, and okay, so that gives us the right side equation. Then the left side of the equation is just our word formula, the force done by kinetic friction times the distance times cosine theta. So we just set up this little diagram here, and since the force done by kinetic friction is in this direction, and then the distance is in this direction, the angle between them. Do you guys have class right now?
That's not the script.
The angle between them is 180 degrees, and cosine of 180 equals -1. So we get negative. I'll just put that in here. So we essentially have a negative over here, which I just used to flip the two halves. Right. Thanks.
Yes.
So
I got
and then
you for
here
now.
we just said h equals d, because if you think about it, once it impacts, how much ever this travels, since it's attached to a string, is the same as how much this will travel. So h equals d. So then we get the coefficient of kinetic friction, mgh, equals big mgh minus this equation for kinetic energy. Once again, we use this -1 to flip the sides of this equation. Alright, go to here.
Yeah.
Alright, so this is the diagram for after impact. So essentially what we're looking at here is, now we're not looking at this at the hanging mass anymore, we're only looking at this. Because as I said before, the block on the table will have some inertia. So we want to calculate the distance it takes to reach a velocity of 0. So just looking at this, the potential energy, we set up a new diagram here such that mu g here is now 0. Because we don't care about, because it's not, there's no movement in the
Which I've already written down.
What'd you write there?
There.
Oh, okay, he already wrote that, my bad. Okay, I think she just wanted us to mark that. Alright, whatever.
Alright, whatever.
So the energy before is still 1/2 mv squared from here. This time, since we're only looking at this block, it's not little m plus big M. The potential energy is 0, we're setting this as 0. And then afterwards, we're waiting till it rests, so it's 0 for both. Once again, we set up our equation. Work done by a non-conservative force is energy final minus energy initial. Once again, that's force of kinetic friction times d cosine theta equals the energy final is 0 minus 1/2 mv squared. And then once again, we can use this diagram again because the force of kinetic friction is that way, and then the displacement is that way. So once again, the theta is 180. So we change this to negative mu k mgd equals -1/2 mv squared from here. Then we just solve for v squared. We do a bunch of algebra combining these two equations, and we get our final answer. And that, for us, that ended up equaling 0.409?
9, I think, yeah.
9 maybe? 9.
Something of that order.
Yeah. So yeah, it's basically how you do it.
Yep. Let's go.